Okay, so on Wednesday we had started discussing the waves in a conductor. And we had seen that the waves in a conductor, they have an exponential decaying factor multiplying this cosine, the traveling wave. So this is basically how it looks like. So you see these lines, these solid, smooth lines, non-straight lines, let's say, almost straight lines, are what we call the envelope. The wave is always within this envelope. And you see that as the wave moves, its amplitude gets smaller, smaller, and smaller. The envelope basically describes how the amplitude changes. So just, this is our z-axis. So this is, you can think of it as a movie in time. Any questions on this? So what we had seen in the case of conducting medium, okay, first of all, our equations were modified, the Maxwell's equations. Now we have a current term. So you see, we had seen that, okay, the divergence of D is equal to 0. We are assuming a neutral conductor. Divergence of B is always 0. Curl of E is equal to minus del B by del T. And the curl of H is equal to J plus del D by del T. And since it's a conductor and the electromagnetic wave contains an electric field, the electric field will generate a current. And the current is, if it's an ohmic conductor, then the current is related to the electric field through the Ohm's law. So sigma being the conductivity. So this is the conductivity, not the surface charge. So also for the surface charge we use the same symbol sigma, but here it is the conductivity, not the surface charge. And then we had seen that, okay, we still have wave solutions, but the wave solutions have some different properties than in non-conducting medium. The electric field we can still write as some vector multiplying e to the power I k tilde z minus omega t, and B is equal to B0 multiplying e to the power I k tilde z minus omega t. These are still valid. I'm just assuming my vector, my wave vector, to be in the z direction. I'm just choosing my z direction to be the direction of this vector. And it just turns out that this k tilde is not a real number in the case of a conductor, and k tilde is just, it has a real part, which is the actual wave vector, the real wave vector, plus I times kappa. Now B0 and E0, they are related through this k tilde vector. And B0 vector is just k tilde vector cross E0 over omega. Now you see, okay, this is in the z direction. That is the meaning of this cross product over here. But you see, it also has a complex phase. This is a complex number. So there is a phase difference between these complex vectors E0 and B0. And this causes the real electric field, the physical electric field. Remember, the physical electric field is just the real parts. The physical electric fields turn out to be some real vector E0 times cosine kz minus omega t plus, let's say, delta E. In general, we also have this decaying factor, whereas the B field is B0. This time this is a real vector times cosine kz minus omega t plus some other phase. Again, it has the same decaying factor, and these phase shifts are related to the phase of this k vector. So let's say this is some magnitude multiplied by e to the power I phi, and delta B just turns out to be phi plus delta E. So different from the waves in non-conducting media, the magnetic field and the electric field in our wave is not in phase. So physically what that means is, for example, if in a non-conducting medium, let's say this is the electric field, and then this would be the magnetic field. They are always 90 degrees to each other. So this is the electric field, this is the magnetic field, and keep in mind that when the electric field is zero, so is the magnetic field. When the B field is zero, when the E field has a maximum magnitude, so does the B field has the maximum magnitude. This is in a non-conducting medium. Now what happens in a conducting medium, let's say this is still the electric field. This would be the magnetic field. So you see, electric field is zero here, magnetic field is zero over here. There's a phase shift, they are shifted relative to each other. Well, of course, I ignored the exponential decaying factor. There's also this exponential decaying factor, so with increasing z, the amplitude gets smaller and smaller. But the phase shift is always there. These are what we had derived on Wednesday. Now, any questions? Now let's look at reflection. Well, the basic principle on studying the reflection on a conducting surface is basically the same as what we did in the case of a non-conductive medium. So you identify the incident wave, the reflected wave, and the transmitted wave, and then you just, on the boundary, you match the solutions on the left of the boundary to the solutions on the right of the boundary. So that's basically what we do. So we will just repeat the same thing over here. Just for simplicity, we will just assume normal incidence, because oblique incidence will not really bring us any new phenomena than what we already know in the non-conducting case and some of the new things that we will observe in the case of the normal incidence. So it's just technically complicated, an interesting challenge question for the homework, but doesn't really, won't really teach us much. So let's look at the normal incidence. So we have two medium, mu1 epsilon 1, mu2 epsilon 2, and let's say this second medium is also conducting. So we have this sigma. We have an incident wave. This is the electric field. This will be the B field. Some of it will be reflected. E1 prime, B1. And some of it will be transmitted. Now, what will be the boundary conditions? So you see, these are what we expect our solutions to be. Now, to determine the reflected wave and the transmitted wave, we just need to match the solutions on the boundary using our boundary conditions. Now, if you go back to our Maxwell's equation in medium, well, let me put rho over here. Well, in the previous case on Wednesday, we studied infinite medium. So the charges will be moving here and there. But as the charges are moving, they started to be homogeneous. They will all move together, neutral, sorry. So as they move around, they will still stay neutral. So there was no free charge. Now, when you have some surface, let's say if you somehow apply some perpendicular electric field to our surface, well, you will create currents. They need not accumulate inside the conductor. So inside the conductor, we still have a rho is equal to 0. But nevertheless, since there is a current and the current comes to in this interface, the surface of the conductor, well, there is nowhere else it can go. So the charges, if they come to the surface, they will stay there. So on the surface, we can still have some surface charge density. So the first Maxwell's equation tells me that the change in the electric field across the surface, let's say epsilon 2e, the perpendicular component, is equal to the free surface charge. Let's say this is 2, this is 1. So this should be equal to the surface charge density, if there is any surface charge density. Well, in our case, there won't be any surface charge density because we are assuming that the electric fields are all in the parallel to the surface. So if they create any currents, those currents will be moving parallel to the surface. There won't be any accumulation of charge on the surface. So this basically reflects in the boundary condition that, well, we have perpendicular components both inside and outside. They are 0 automatically. There's no perpendicular component. So basically, in this problem, we derive the fact that there won't be any surface charge. Of course, if you look at oblique incidence, not normal incidence, but oblique incidence, it is possible that we will end up having some surface charge density. Yes. So the electric field is perpendicular to the normal direction. So there is no component of the electric field perpendicular to the surface. In the case that we are studying, not in general. If you just if this is your surface, if you send your wave in an oblique incidence where the B field is parallel to the surface, just like the example we studied in the case of non-conducting media, the electric field both had a normal component and a perpendicular component, and this perpendicular component could create some surface charge density because it will cause charges to move perpendicular to the surface, so some charge will be accumulating on the surface, or there will be a depletion of charge on the surface. That is something you need to take into account if you study the oblique incidence on a conducting surface.
Hocam şimdi elektrik alanı paralel ya, bu yüzeyde yukarı doğru bir yüzey akımı oluşturmayacak.
Of course, there will be a surface current in the upward direction. Its divergence will be 0 because it's proportional to the electric field. Electric field has 0 divergence, so there won't be any free charges. You see, it's just like this. You have this, let's say, you have this surface. All the charges are moving horizontal to the surface. Well, there's no accumulation of charge. So charge density will not change. It started to be 0, it stays to be 0. If this is your surface and you create a current in the vertical direction, up or down, then of course the charges cannot move across the surface. So if there is a current, upward current, charge will start accumulating on your surface. Or if there's a downward current, there will be a depletion of charge on the surface. And hence there will be some negative charge accumulating on your surface.
What happens if it is 45 degrees, for example?
Well, I don't care what the angle is. Whatever the electric field is, I can always write it as a sum of a component that is parallel to the surface, which won't create any surface charge, and the component that is perpendicular to the surface, which will create a surface charge, which might create a surface charge, let's say. But in this example, there's no problem. The electric field, we start with an electric field that is perpendicular to the surface, so there's no surface charge.
So in this problem, just we take to the perpendicular component of the electric field and write this equation.
True. Of course, in that case, you have one more unknown, the surface charge. So since you have one more unknown, you hope that you will have one more equation. Well, let's see, del dot B is equal to 0. This is always the case, just like in the non-conducting case. This is also true. So B perpendicular is continuous. Well, this is already satisfied by our solution. There is no perpendicular component of B. Now let's come to the other two cases. Curl of E is equal to minus del B by del T. Well, this tells me that the parallel component of the electric field is continuous across my surface. So let us see what are the parallel components of the electric field. I have E1, e to power I k1 z minus omega t. This should be plus E1 prime, no, E1 prime. Well, let me put the 0 also here. E1 0 prime, e to power I minus k1 z minus omega t. This should be equal to E2 0, e to power I k tilde z minus omega t. This should be valid at z is equal to 0. That is my surface, my interface. This is z is equal to 0 surface. So you see, at z is equal to 0, these factors are just 0. So these factors are 1. I can cancel the time dependence. So I have E1 0 plus E1 0 prime should be equal to E2 0. This is one equation I have. Or let us just assume that the electric field is in the x direction. This just tells me that these numbers, E10 and E10 prime, they should add up to give E20. What I'm doing is exactly the same as what I did in the case of a non-conducting medium. And this equation is in fact exactly the same as what we had in the non-conducting medium case. Now let's come to the last equation. Curl of H is equal to J times J cross divergence of the derivative of T. Now that tells me that the parallel component of H can be discontinuous. It is possible if there is a surface current. But you see, we know that J is equal to sigma times E. If there is a surface current, J corresponding to that surface current will be, let's say, some K Dirac delta Z. So here K is my surface current. It only exists when Z is equal to 0 on my surface. But you see, this tells me that J is infinite on the surface. If J is infinite on the surface, that tells me that the electric field is infinite on the surface. Well, that just cannot be. is finite on the surface, if I just combine all of these, K is equal to 0. So there is no surface current. Although in principle, well, you see, I can have current running very close to the surface. But what we mean by a surface current is a current that is only on the surface, that doesn't have any extent, any volume, just an area. So although in principle, parallel component of H might be discontinuous, you see we are talking about conductors, so in principle you might create circumstances in which there will be a surface current, but to create that you need infinite electric field on the surface, which at least in this case we don't have it. So there is no surface current, although we are talking about conductors, still there is no surface current. So the parallel component of H is continuous. This just tells me that B parallel over mu is continuous, or B1, B1 0 in the y hat direction over mu1 minus B1 0 prime in the y hat direction over mu2. This should be equal to B2 0 in the y hat direction over mu2. Well, this is mu1, sorry. Well, why did I have that minus sign over here? Just check my definitions of direction in the above part. You see, when the wave is moving in the backward direction, in the minus z direction, I still, just for demonstration, I just chose E1 prime to be in the upward direction, so B1 should change its direction when it's reflected. Again, this is exactly equal to the expression we had in the non-conducting case. Basically, up to this point, nothing changes between a conducting case and the non-conducting case.
Yani hocam şurada şimdi J sıfır değil mi?
J is non-zero. You see, J is just sigma times E.
Ama hocam K'de sıfır deyince, hani surface current sıfır deyince J'de sıfır olmuyor mu şurada?
Not necessarily. You see, we can have J inside the conductor. There is nothing that prevents that. But on the surface, there is no finite current. Yes. So there is no current on the surface. So K is 0 on the surface. J is the volume current density. You see, volume current density and surface current densities are different things. You see, just take a very thin slab of material. Okay? If you multiply J by the thickness of this material, you kind of get the current density running over this volume. Now, a surface current is what remains from this current when you send the thickness to 0. So if the current is finite everywhere, when the thickness goes to 0, well, the current is finite. You are multiplying it with 0, you get 0 surface current. You can think of, maybe it's easier to think of in terms of the current densities. You see, we have the current density, and we also talk about the volume current density. You can have a homogeneously charged sphere, for example. It will have a current density, but it will not have a surface current. It will have a charge density. It will not have a surface charge density. The charge density, that doesn't mean that the charge density is 0 on the surface. It just means that if you take a very thin shell on the surface, its charge will be negligible. Just similarly, there can be a current running in my conductor. Some of that current will run very close to the surface. But if I take a very thin volume very close to the surface, very thin, If the volume is negligible, the current running through that volume is negligible. That is what we mean by when we say that there is no surface current density.
I don't understand how K is 0.
How what?
How K is equal to 0? For J is equal to sigma E equal to K delta of Z.
You see, this is how we define the surface current. So if we have a surface current K, we can always write it as a volume current, just by multiplying it with Dirac delta. So this is just basically a current that is running only on the surface. It has this is a current density. It gives a finite current in total. So it has to be infinite at that very thin region. So that 0 times infinity, it will give me a finite current. But you see, I also have this relation. So at Z is equal to 0, my current density is infinite if I have a surface current. But if the current density is infinite, that means the electric field should be infinite. But the electric field is oscillating, its magnitude doesn't really change. So if it's infinite on the surface, it's infinite everywhere, more or less. But I know that I'm talking about finite electric fields in this case. Since the electric field is finite, J has to be finite everywhere, including Z is equal to 0. That is only possible if K is equal to 0.
O zaman gerçekte biz hiç bir zaman için surface current elde edemiyoruz.
Well, real surface currents are just do not exist anyway. So realistically, the current is always a distribution. The charge density is always a distribution, but the current can be spread over a very narrow sheet, for example. You can just approximate that sheet to be an ideal surface. In that case, you get a surface current density or a surface charge density. But in this case, even in that idealization, we don't have that one.
Faz farkı nerede oluşuyor?
Well, the phase difference between the E and the B. Oh, you mean where does it physically? Right on the surface there is a phase difference. You see, on the left, in this region, there is no phase difference between an E and the B field. On the right, there is a phase difference between the E and the B field.
Elektrik alanları için sigma bir eşitlik. Burada niye reflection'a bakmıyor? Reflection elektrik.
Well, you see, what I mean by electric field in region 1 is the total electric field on the left-hand side. And this is the total electric field on the right-hand side. This result is valid even for this is valid for any electric field, in fact, not just waves. For any electric field, we have this relation. Now, in our case, we have this electromagnetic waves with normal incidence. So these components are 0, and hence we conclude that the free charge density is also 0. Although there is a conductor there, and in principle we are considering the case that we can create currents running in the conductor, and those currents can carry the charge on the surface, creating a surface charge density. In principle, it is possible. But in this particular case, we just have seen that it doesn't happen, because the electric field doesn't have a component perpendicular to the surface. Yes?
Faz farkının olması için E'nin komponent ya da B'nin beraber komponentlerden birisinin discontinuity'sinin bozulması gerekiyor.
Well, you see, what do you mean by continuity and discontinuity? Those are also things that you have to pay attention to. You see, the incident wave, the reflected wave, as the incident wave is reflected, there is no continuity in the B field. B field was pointing in this direction on one instant, and it's just pointing in the opposite direction in the other instant. But what we mean by continuity is, let's say, the total B field at this point. which is the sum of these two, should be equal to, mu, B over mu, should be equal to the B field on the other side. And similarly for the electric field, the sum of these two should be equal to the E field on the other side. So when we are talking about continuity, there are various things that you can talk about being continuous or discontinuous. These conditions that we are writing, these boundary conditions, over here, they relate the total electric or magnetic field on one side of the surface to the total electric and magnetic field on the other side of the surface. Those should be continuous, or if there are surface charges, surface currents, or discontinuous by the given relations.
Hocam bir de şurada K1, XK1'de şurada K tilde var. Hani bu exponential'lar nasıl sadeleşti?
Z is equal to 0. This equality should hold on the surface. That is at Z is equal to 0. At Z is equal to 0, K2 tilde Z is 0, K1 minus K1 Z is 0, K1 Z is 0. What we are cancelling actually is e to power minus I omega t from this term, e to power minus I omega t from this term, and e to power minus I omega t from this term. Those are the things we are cancelling. Okay, now let's continue with this one. You see B10. How is it related with E10? One over V, V1, the speed of the electromagnetic wave in medium 1. B10 prime, it's also E10 prime over V1. B20 is E20 multiplied with K tilde over omega. So that is what we need to put over here now. So these are the relations we have. E10 over V1 mu1 minus E10 prime over V1 mu1. This should be equal to K tilde over omega mu2 E20. Or E10 minus E10 prime. This is equal to beta E20. Well, let me put beta tilde. Beta tilde is equal to K tilde over omega times V1 mu1 over mu2. Well, in your book, the book quite often uses this tilde to denote complex quantity. So beta tilde is a complex number over here. You see, again, up to this point, everything is almost identical to the non-conducting case. The only difference that appears is that beta tilde is now a complex number. Before it was a real number, now it's a complex number. Sorry?
Genelde real number'la ilgileniyorduk hani dalgalarda. Şimdi kompleks number nasıl?
You see, look at this relation. E20 is not the amplitude of my electric wave. The magnitude of E20 is the magnitude of my electric wave. The E20 is a complex number in general, to start with. Similarly, B20 could have been a complex number in general. So basically, once we calculate E and the B fields in our complex notation, to obtain the physical part, at the end, we have to take the real part. So this basically, this K tilde being complex basically tells me that there is a phase difference between the electric and magnetic fields. So I will do all these calculations, and to get the physical fields, at the end, I have to take the real and the real part of the electric and the magnetic field. So there is no problem with beta tilde being complex. Just keep in mind that at the end, we will take the real part to obtain the physical electric field. And what else we have? We have E10 plus E10 prime. This should be equal to E20. And we can just solve these equations. Let me write it in this form. Beta E20 plus E10 prime. E10 is at the same time E20 minus E10 prime. So if you just sum them up, you will obtain E20 is equal to 2 over 1 plus beta tilde E10, and E10 prime is equal to beta tilde minus 1. No. E10 prime is E10 minus E20. No, E20 minus E10. From this equation, E10 prime is just this minus this one. We already had determined what E20 is, and this becomes 1 minus beta tilde divided by 1 plus beta tilde E10. So we know the reflected wave, we know the transmitted wave, etc. Okay, so what can we say? Well, let's look at beta tilde. Well, beta tilde, all these are real numbers, is proportional to k tilde, and we had seen that k tilde is equal to k plus I kappa. And furthermore, kappa is proportional to sigma. You can just look up the explicit expressions. Let's say we are looking at a perfect conductor. A perfect conductor is one for which sigma is infinite. So k tilde is infinite complex. Beta tilde is infinite. So for a perfect conductor, the transmitted wave, you see beta tilde is infinite, so E20 is 0. E10 prime, beta is infinite, is minus E10. So all the wave is reflected. No change in the amplitude of the incident wave, nothing goes through. Well, that's what we call a mirror.
Manyetik alan da mı? Tamamen. Manyetik alan da mı tamamen reflektif?
Well, you see, the E field and B field, they are related to each other. If the E field is perfectly reflected, so it should be the B field. I mean, the E field and B field, you cannot separate them. You see, if you look at these ones, you see B10 is given by that expression. Well, E10 prime magnitude is equal to E10, so B10 prime magnitude is equal to B10. So all the wave is reflected completely back. And that is why the good conductors the metals make good mirrors. So So when you want to make a mirror, you basically, well, you don't want to use too much metal. It becomes heavy, it becomes expensive. So what you do is you just get a glass or any other transparent material, cover one side with a metal. It also prevents oxidation. And that is how you get metal, how you get a mirror.
Hocam bu beta tilde peki sıfır olursa ne olur?
Well, let's see. Is it possible for beta tilde to be zero? Is beta tilde has this relation. Beta tilde is proportional to k tilde. Well, V1, mu1, mu2, and omega, they are all constants. So if beta tilde is zero, that basically means k tilde should be zero. If k tilde is zero, both its real and imaginary parts should be zero. Well, the imaginary part is zero if there is no conductivity. But if there is no conductivity, then k is just a function of omega and v. K is just omega over the velocity, the speed of the electromagnetic wave, none of which is zero. So you cannot have k tilde equal to zero. But we will look at some more weird cases.
Hocam matematiksel olarak E1 prime eşittir eksi onu yapmamız doğru mu? Eksi sonsuz daha sonsuzu şey yapmış olmadık mı?
Why? E10 is a finite quantity. It's not infinite.
Baktığımızda bir önceki ekspresine baktığımızda gerçekten oldu. Hemen aşağıda.
This one. Well, your friend has a point. You see, what we are looking at is what happens when beta tilde is infinite. Well, beta tilde is infinite, so something should be infinite. Or something should be zero. You see, if this equation is to hold even when beta tilde is infinite, that basically tells me that E20 should be zero. That is what we obtain. E20, when beta goes to infinity, just becomes zero. But we also cannot just set E20 equal to zero to start with, because in that case, E10 minus E10 prime will be zero, and E10 plus E10 prime should be zero, it seems. We cannot just set it equal to zero, but when we are taking the limit, we should take the limit in such a way that this goes to infinity, this goes to zero, the combination should be finite. And basically that is what we obtain over here. If you multiply E20 by beta tilde and take the limit that beta tilde goes to infinity, what you get is twice E10. So this quantity over here in the beta tilde going to infinity limit is finite.
Yani o E10'nun iki katına mı denk geliyor?
This combination in the limit when beta tilde is infinite, or when we apply this formalism to a very good conductor, this product turns out to be almost equal to twice E10. Well, that is kind of expected because E10 prime, we just found out that that is minus E10. So this is just twice E10. And that is only possible, this combination is a finite quantity in a very good conductor only if this is almost zero. E20 is almost zero. That also tells me that E10 prime and E10, they should be of opposite sign. Now, I don't remember the exact expression now, but if you would just go back to our lecture notes on the previous day, you will see that K We had obtained the value of k, and k just turned out to be omega over c twice v 1 plus square root of 1 plus some function of omega. Yes, k squared is omega squared over twice v squared. So this was what we had obtained for k squared. Now the exact expression, I will not really need it. The thing is, you see, k is a function of frequency. That is what we basically call a dispersive media, a dispersion. It just tells me that k over omega squared, this is 1 over twice v squared 1 plus square root of 1 plus a of omega. Well, k over omega for a vector is the inverse speed. So the speed, the wave speed, depends on the frequency. So such medium is what we call dispersive medium. Now, in this example, the reason of dispersion was due to the conductivity of the medium. We were dealing with conductors. Now we will look at another source of this. In the next hour, we will look at another source of dispersion, and where it is the epsilon will actually be a function of omega, of the frequency. Now we will see how that comes out in a simple model, and then we will just look at the consequences. So basically, this frequency dependence of epsilon, or more precisely the refractive index, we will see that it also has real and imaginary parts due to this frequency dependence. And that is what causes some materials to be transparent, some materials will be opaque, some materials will be non-transparent. So at least now we have an explanation why conducting surfaces are shiny. Now we will try to understand why some materials are transparent like glass, some materials are opaque, it just lets very small amount of light but not much, and some materials don't let anything pass through.
Hocam bu elektromanyetik force değil mi?
No, this is the electric permittivity. Well, you see, if you take a glass, just rotate it around, you will see a black thing covering the backside of the glass. That black thing is nothing but oxidized metal. So basically what you do is you just take a piece of glass, which is transparent, you cover the backside with a metal, a very thin layer of metal. The part that is facing the glass doesn't get oxidized, it doesn't, there's no oxygen in that, between the layer and the glass, so it's not oxidized, so the surface is a very good conductor, so it reflects most of the incident light. So when you look through the glass, you see yourself. Well, you see, the thickness of the metal doesn't really care. We don't care about that because the electromagnetic field cannot penetrate. You see, E20, that is the transmitted wave for a very good conductor. Well, that is negligible. So whether you have a very thin sheet of metal or a very thick sheet of metal doesn't make any difference. The electromagnetic wave does not penetrate. For example, just take an aluminum foil. A very thin sheet of aluminum foil reflects good enough. When you roll it up, you get very thick aluminum. It reflects the same. Okay, let's give a 10-minute break and then we will continue.